So let's see how you solve this now with reducer hyperobjects. Okay. So first of all, what is a reducer? So a reducer over a type T, it's a kind of hyperobject which has a member function reduce that implements a usually associative binary operator, which I've drawn as star times, and its constructor implements an identity. So this operator could be, for example, addition with the identity 0. Could be multiplication with the identity 1. It could be maximum, okay, with the identity minus infinity. There are a variety of different ways that you can interpret what this is. And the important thing is that T has to have a reduce function that implements that operator. Okay? When we say it's typically associative, we mean back to elementary algebra that that this identity holds, that A times the quantity B times C is the same as A times B, that quantity times C. When we say it's an identity, we mean that that if you operate with any other element, you get back the element. Now, the way that you use a reducer is you declare X, if you wanted to make that be a reducer, you declare X to be a hyperpointer to this type T, which has this member function. And what that does is it instantiates X as a hyperpointer to a reducer of type T. And it initializes X to be the identity. Okay? And then whenever you dereference X, it produces a local view of the reducer. Okay? And views can differ from point to point in the program, but during execution, the Cilk++ runtime merges these views using the reduce member function. So this is kind of abstract, so let's dive down and look at a specific example. And you see this is actually a lot easier to understand in the context of an example. So here's our example back. So now what I'm going to do is I'm going to instantiate the hyperpointer, okay, to make result be a hyperpointer, okay. And what I'm going to do is use one of the library functions, reducer op add, which is the addition function, okay. And this is built in on int, okay. And so what that does is it says, okay, result is a pointer to a value that I'm going to be summing. And so whenever I access it, I have to dereference it before I access it. So there, I also have to do a star here, and here I'm doing a get value in order to produce the proper result because I've added a level of indirection here. So I guess I should say here. So this is all you need to do to parallelize it. Is basically identify that result is something that everybody's adding into. That's it. And now just where you add it, where you access it, you have to add one level of indirection. If in many common cases, the thing that you're accumulating into, you already have a pointer to it. And then you don't have to worry about it at all because you don't have to worry about that extra level of indirection because you've already got it there. Here's a more complicated example that shows the power of the hypervariables. And that's doing collision detection in a mechanical assembly. So the idea is, suppose you have assembly represented a tree of sub-assemblies. So a pickup truck is represented as a body and a chassis, engine, and drivetrain. And each of those is broken down to its component parts and so forth, down until you get some sort of complex geometric object representing, atomic parts. So the goal in this particular example is going to find all collisions between an assembly and some target object. So you're given one object. So that object, for example, maybe you're trying to drill through everything, and you want to know what are all the parts that you hit when you drill through them all. Okay, which I guess, given the price of gas, is what some people would like to do with their pickup trucks these days. Okay, so here's a piece of C++ code that, a sketch of C++ code that implements that. So we're going to try to create a list of all the parts in the mechanical assembly that collide with the given target object. So we have our node, we have a target, and we're going to accumulate an output list of all the things that happen to intersect with the target. And the way we're going to do that is we're going to do a walk of the node of this graph. We're going to take, during this node walk, we're going to look to see whether we're at an internal node that is a subassembly that has parts, or at a leaf. Okay, so that's the internal node, or at a leaf, meaning we've got an atomic part. If we're at a leaf, what we'll do is check to see if the target collides with that leaf, and if so, we add that element onto the output list. If it's an internal node, then what we do is we run through all the children from beginning to end, incrementing, and then recursively walk the child. So we can parallelize that by using the Cilk 4, okay, just to parallelize the parallel walk. Okay? And in this is using Cilk 4 loop, where we're able to iterate over more general structures. But basically what it's doing is it's now going to visit all those children in parallel. Okay? And then walk them all in parallel. So they all are able now to go and do their recursive walks and do their collision detection. But the problem is that we now have a race bug, because everybody's trying to push their results onto the output list. So we could go through the same thing. We could put a lock around this, and then we have lock contention. We'd probably get no parallelism out of it. Okay. Instead, what we'll do is we'll use a reducer whose reduce function concatenates lists. Okay, and that we can use using the built-in reducer list append type. And what we'll do is now, instead of having output list dot pushback, we have to add the arrow to indicate one level of indirection to access it. Okay, and now turns out this code now will correctly walk the list, because what's happening is the list concatenation, turns out, is an associative operation. So if I concatenate list A with list B, and then concatenate C, that's the same as if I concatenated A to the concatenation of B and C. And so therefore we're able to produce this list automatically in the Cilk system without having to do any substantial code rewriting. Just simply putting in this declaration where the value was declared, and then using the Cilk 4 and adding a level of indirection in the plate points where we're accessing it. So Cilk++ provides a hyperobject library containing many commonly used reducers, okay, including the list append, which I just mentioned, prepend, max and min, and also getting the index of the element, which is a max or min, the add function, which we talked about before. We also have an output stream. We have some basic string operations with string concatenation and so forth. And also, it allows you to write your own. So if one of the ones isn't in the library, you can write your own, or you can tell us, which is good too, and if it's a common enough one, we'll add it to our library. So just to conclude at this point, brief summary. There's 3 keywords that you have to know. Okay? When you sharp define the spawn and sync to null and the 4 to the Cilk 4 to be 4, you have a serialization, and every Cilk++ program has a serialization. You should make sure that when you spawn off parts that they're independent, or generate them parallel with Cilk 4, that they're independent, and there's no data races between them. But if you do have data races, you can pick them up. And then you can use reducers to mitigate races on global variables without lock contention or logical restructuring. So we have a few exercises that we've prepared for you. One is to Cilkify quicksort on your own. Okay. Second one is to look at Cilkifying the outer loop of a matrix transpose. And the third one is to Cilkify an application using a reducer.